such coefficients affect how such physical parameters how such coefficients affect the physical parameters such as the energy. These fractional deviations are known as the dephasing coefficients, and the phasing coefficients consist of the post-Newtonian coefficients, namely delta chi sub 0 to delta chi sub 7, the phenomenological coefficients, delta beta sub 2 and to delta beta sub 3, and the analytical black hole perturbation theory parameters, namely alpha sub 2 to alpha sub 5. To better illustrate how the change in dephasing coefficients alters the waveform, we plot the phase of the gravitational wave versus time. In this figure, we have the phase evolution of the IMR phenom PV2 waveform with varied dephasing coefficients. A dephasing coefficient is chosen from each regime to illustrate how the dephasing coefficient changes the waveform and hence the physical parameters. More specifically, in this figure, we illustrate how the dephasing coefficient changes the phase of the gravitational wave. In this figure, on the other hand, we changed the same dephasing coefficients as those in the previous figure. However, this time, we plot the strain versus time. This figure serves to demonstrate how the dephasing coefficient changes the shape of the gravitational waveform. Note that the deviation in these two figures have been exaggerated to make the deviations more visible. In reality, such large deviations have been ruled out by observation. Now we talk about the multipole expansion of energy. To compute the energy carried by a gravitational wave, we take the 0,0 component of the Isaacson stress energy tensor and integrate over the volume. Here, H plus and H cross are the plus and cross polarization of the gravitational wave respectively, and the overdots represent the derivative with respect to coordinate time. To obtain an analytic expression for the integral over solid angle, we have to separate H plus and H cross into a time-dependent and an angular part. This can be done using spin-weighted spherical harmonics. And for outgoing gravitational waves, we are concerned with the S equals -2. Here, the second line has been truncated because for align spin binaries, H22 and H2-2 are the leading order terms in the multipole expansion. Integrating over solid angle, we obtain the instantaneous power. However, to avoid calculating the average over several wavelengths, one approach is to numerically calculate the cumulative energy, which is simply this. Equipped with the expression from the previous slide, we can now explore how the intrinsic parameters affect the radiated energy of the gravitational wave. In our project, we explore how many different intrinsic parameters, such as total mass, mass ratio, and spin, affect the gravitational wave. However, for the sake of simplicity and saving time, we are going to use total mass as an example. As seen in this figure, the radiated energy increases. The radiated energy of the gravitational wave increases with the total mass. It is important to note that the waveform used in plotting the current figure has been tapered to exclude the unphysical artifacts that comes with IMR phenom PV2 waveform. To check whether our results make sense, we compared the total radiated energy to that of a real GW signal, namely GW150914. To clarify, the LVK teams do not directly measure the energy. The calculations done by the LVK team are inferred using the same equations mentioned in the previous slide. Therefore, we are merely checking our calculations with that done by the LVK team. We can see from this figure that for a binary system of Q equals 1 and M equals 60 solar masses has a radiated energy of about 2.5 solar masses times the speed of light squared. Comparing this to GW150914, which has component masses of M1 equals 35.6 and M2 equals 30.6 and a mass ratio of 0.85, the total radiated energy is about 3.0 plus or minus 0.5. And from this, we can see that our results agree with the LVK analysis team as the component masses, the radiated energy, and the radiated energy are within the margin of error. Another thing we can see from this figure is that the total mass has a major effect on the cumulative energy in the intermediate and the merger ring down phase. However, more interestingly, the cumulative energy in the in-spiral phase seems to have little to no variation when plotting in linear scale. To more clearly illustrate this, we plot the energy during the to more clearly illustrate the change in energy during the in-spiral phase, we plot this figure in logarithmic scale. As we can see from this figure, in the in-spiral regime, the total mass and the radiated energy share an opposite correlation to that in the previous figure. Here, the total mass radiated energy seems to decrease with the total mass, seems to decrease as the total mass increases. Now we get to the main meat of the project, and we will explore how the energy evolves over time with the varying dephasing coefficients. The dephasing coefficient that we focus on are the ones that affect the in-spiral phase, namely delta chi sub I. For a better display of the results, we do not plot all the energy versus time graph of all delta chi sub I. Instead, we choose to plot one with high p-n order and one with low p-n order. Here we choose delta chi sub 1, which corresponds to 0.5 p-n order, and delta chi sub 7, which corresponds to a 3.5 p-n order. As shown in this figure, the radiated energy has little to no variations, little to no change in the merger ring down phase, but has noticeable change in the in-spiral and intermediate phase. This is expected as delta chi sub I affects the dephasing, affects the waveform in the in-spiral phase. For 3.5 p-n order case, we can see a similar trend where the radiated energy has little to no variation in the merger ring down phase, but has noticeable change in the in-spiral and intermediate phase. Again, this is to be expected as delta chi sub I are associated with the waveform in the in-spiral phase. For a better visualization for the change in energy during the in-spiral phase, we can plot the previous two figures in logarithmic scale. From this figure, we can see a general trend that the higher the absolute value of the dephasing coefficient, the higher the energy during the in-spiral phase. The same trend can be seen for higher p-n order. Moreover, notice the line for, notice the line for delta chi sub 1 equals 1 and delta chi sub 7 equals 1. We can see from this figure that there is a larger deviation for the lower p-n coefficients. So this implies that the dephasing coefficient when the dephasing coefficient varies, the higher p-n order, the smaller the deviation from the GR predicted waveform. Again, such large deviations such as 10, 100, and 1000 have been ruled out by observations, and the sole purpose for plotting them is to better visualize the change in energy. Now we turn our attention to obtaining a more quantitative trend between delta chi sub I and the cumulative energy. To do so, one would think of plotting the entire waveform, the cumulative energy of the entire waveform versus delta chi sub I. However, if we go back to this slide, we can see that this is not such a sensible approach, as during the merger ring down phase, the total radiant energy has very little variation. So this small variation will lead to complications in the later stage, as it is hard to bound delta chi sub I using small variations in the physical parameters. Therefore, the more sensible approach is to bound delta chi sub I by the energy is to plot the peak energy during the in-spiral phase. To do so, we restrict the radiated energy to those in t less than -3. However, this restricted region of time is only exclusive to the case where m sub 1 and m sub 2 equals 60 solar masses. For different set of intrinsic parameters, one would have to tune the time restriction such that the variation in energy is sufficiently large. To illustrate how the p-n order affects the total energy of the gravitational wave, we plot the energy versus delta chi sub 1 and delta chi sub 7 as example. This is for delta chi sub 1 and this is for delta chi sub 7. As seen in these two figures, for both low and high Pn order, the radiated energy during the in spiral phase roughly increases with the absolute value of the dephasing coefficient. The word roughly is used because the minima of the distribution is not centered at 0, at delta chi equals 0. However, despite the fact that both delta chi sub 1 and delta chi sub 7 increase with the radiated energy, the rate at which they increase is very different. As seen from this figure, the distribution for the energy versus delta chi sub I, the graph has a much narrower width and has a sharper peak for when the dephasing coefficient deviates from the GR predicted value. However, for this case, we can see that the cumulative radiated energy during the times for t less than -3 seconds increases more gradually with the dephasing coefficient than the previous slide, as the shape of the distribution has a broader width. This implies that the dephasing coefficient that correspond to a lower Pn order is more sensitive to change in the radiated energy. Now, to bound the dephasing coefficient, we set a bound on the cumulative energy. For example, we can bound it by something like, if we bound the energy by 10 to the -3 seconds, we can see that the allowed values, these are the allowed values of the dephasing coefficient. As we can see, by varying, let me get rid of this first. As we can see, by varying the intrinsic parameters and the dephasing coefficient corresponding to the in-spiral part, we saw how such variations affect the evolution of energy over time. In the future, we will focus on extending similar analyses provided in this project to the intermediate and the merger ring-down phase. After this, we vary the intrinsic parameters and the dephasing coefficient to see how they affect the evolution of angular momentum. From there, we plan to use these physical quantities, namely the energy and angular momentum, to constrain the dephasing parameters. I would personally like to thank Alan and Rico for their supervision and guidance throughout the project. And I would also like to thank my CUHK mentor, Tjonnie Lee, for helping me arrange the LIGO SURF program in the first place. I would also like to thank the National Science Foundation for supporting the LIGO SURF program. And finally, I would like to thank all those at LIGO SURF that made the experience so worthwhile. Now I'll be taking questions from the audience. Thank you, thank you.
Thanks, Leif. Any questions? I'll probably have to repeat them. Yes, Alan.
Thanks very much, Leif. That was great. Do you have did you experience any challenges with regard to your computational resources? Was it hard to do these computations on your laptop? Did you need a cluster?
I generally use the LIGO cluster that is provided. It wasn't too difficult, actually. But I think in the future, when we actually do the, well, I guess what I'm saying right now is what we have done so far is the forward mapping. Like what we've done is showing that the dephasing coefficient actually affects the physical parameters. When we do the inverse mapping, when we take the physical parameters and bound the dephasing coefficient, I think that will be the computationally challenging part.
Sounds good. Thanks. I actually have another question, if you don't mind.
Sure.
You've been focusing on the energy and the angular momentum. Which is powerful, but it's also kind of we don't directly measure it really. What we do directly measure are, of course, the waveforms, and in particular the parameters like sharp mass or total mass, which we do separately for in spiral and then for merger and ring down as a test of GR. And maybe if you focused on, and of course you could do it in separate pieces of the in spiral. And so maybe it would be also of interest to explore our ability, comparing our measurements of, for example, the total mass in spiral merger and ring down. You might have other interesting constraints on these dephasing parameters.
Okay.
And we can talk about this later.
Yeah, sure, no problem. By the way, I just have some references as well, so yeah, just important to show that.
Any other questions? If not, let's thank Leif again. And
Thank you so much. Thank you.
he goes next. Are these in order?
No, that's the
there?
prefix, opposed to